In statistics, the T-statistic is a ratio of the departure of an estimated parameter from its notional value and its standard error. It is used in hypothesis testing, for example in the student unregistered trademark ST test, in the augmented Dickey Fuller test, and in bootstrapping. Definition: let be an estimator of parameter I squared in some statistical model. Then a T-statistic for this parameter is any quantity of the form where I squared 0 is a non-random, known constant, and is the standard error of the estimator. By default, statistical packages report T-statistic with I squared 0 equals 0. However, when T-statistic is needed to test the hypothesis of the form HO, I squared equals I squared 0, then a non-zero I squared 0 may be used. If is an ordinary least squares estimator in the classical linear regression model, and if the true value of parameter I squared is equal to I squared 0, then the sampling distribution of the T-statistic is the student unregistered trademark ST distribution with degrees of freedom, where n is the number of observations, and k is the number of regressors. In the majority of models the estimator is consistent for I squared and distributed asymptotically normally. If the true value of parameter I squared is equal to I squared 0 and the quantity correctly estimates the asymptotic variance of this estimator, then the T-statistic will have asymptotically the standard normal distribution. In some models the distribution of T-statistic is different from normal, even asymptotically. For example, when a time series with unit root is regressed in the augmented Dickey Fuller test, the test T-statistic will asymptotically have one of the Dickey Fuller distributions. Use: most frequently, T-statistics are used in students' T-tests, a form of statistical hypothesis testing, and in the computation of certain confidence intervals. The key property of the T-statistic is that it is a pivotal quantity while defined in terms of the sample mean. Its sampling distribution does not depend on the sample parameters, and thus it can be used regardless of what these may be. One can also divide a residual by the sample standard deviation. To compute an estimate for the number of standard deviations a given sample is from the mean, as a sample version of a z-score, the z-score requiring the population parameters. Prediction: given a normal distribution with unknown mean and variance, the T-statistic of a future observation after one has made n observations, is an ancillary statistic a pivotal quantity that is a statistic. This allows one to compute a frequentist prediction interval, via the following T-distribution. Solving for yields the prediction distribution, from which one may compute predictive confidence intervals given a probability p. One may compute intervals such that 100% of the time, the next observation will fall in that interval. History: the term T-statistic is abbreviated from test statistic, while student was the pen name of William Seeley Gossett, who introduced the T-statistic and T-test in 1908, while working for the Guinness Brewery in Dublin, Ireland. Related concepts: z-score: if the population parameters are known, then rather than computing the T-statistic, one can compute the z-score. Analogously, rather than using a t-test, one uses a z-test. This is rare outside of standardized testing. Studentized residual: in regression analysis, the standard errors of the estimators at different data points vary, and thus one must divide the different residuals by different estimates for the error, yielding what are called studentized residuals. See also: F-test, student's T-distribution, student's T-test. References. External links.